Hello everyone, today I will present our work ELISE, a storage-efficient logging system powered by redundancy reduction and representation learning. Many systems and applications collect logs to support security analysis. For example, Linux, Windows, and MySQL collect logs for intrusion detection and debugging. However, collecting logs can result in high storage overhead. As reported by previous work log Gzip, a server can generate more than 3 GB log data in one day. The work from Xu also demonstrated that in 1 year, the enterprise needs to collect more than 17 petabyte log data. The recent work SEAL also shows that a small number of computers can generate 50 GB log data in one day. To reduce the storage cost, some pruning methods remove redundant events in logs without affecting the final results for specific tasks. For example, when a process reads a file many times, we can remove repeated activities for dependency analysis tasks. However, they are usually not practical for general tasks because they lose important information, such as repeated events for frequency-based intrusion detection methods. Another solution is compression, which uses fewer bits to represent the original data. Lossless compression removes unnecessary information in the original data without affecting the overall results for a specific task. This kind of method is similar to the pruning method and cannot be applied to general tasks. Another kind of method is lossless compression, which uses short encoding to represent the original data. The compression keeps all information in the original data and is more suitable for log compression. Here, we introduce a lossless compression method called Gzip. Given the original log, Gzip first does preprocessing to replace repeated strings with short marks. Then, Gzip encodes the log into a shorter representation. It first creates a Hailun tree based on the frequency of characters in the file, and generates a Hailun reference table. In this table, a more frequent character is encoded with less bits. Finally, Gzip encodes the original log by replacing the characters with short codes in the Hailun table. According to the preprocessing and the encoding, Gzip removes most of the redundancies in log and achieves good results. Recently, a deep neural network-based encoding method called DeepZip is proposed to achieve better compression results. Unlike Gzip, which encodes characters based on their frequencies in the file, DeepZip trains a deep neural network to encode the data. Given the original data, the deep neural network model predicts each character and outputs their prediction values. Based on the prediction results from the model, arithmetic encoding encodes the characters with fewer bits. As shown by many existing work, deep neural network-based method can achieve better encoding results. Although DeepZip can provide better encodings, it doesn't initialize domain knowledge in log redundancies, and doesn't have a pre-processing step. Training a deep neural network-based encoder on the entire log file is time-consuming. Therefore, we want to explore more log redundancies in preprocessing and design a better deep neural network encoder. Based on these ideas, our method achieves the best compression ratio, which is defined as the compressed file size over the original file size. Compared with the existing work, our method can achieve 13 times better compression ratio on some datasets and is around 7 times faster compared with DeepZip. Our system, which is called ELISE, consists of 4 components. First, it receives logs from different sources. A log formatter then converts logs into JSON files and splits the file into several parts for more efficient processing. Then we design several processing rules to remove log redundancies and create a reference table for these rules. After that, we train a deep neural network encoder. And finally, arithmetic encoding algorithm takes the prediction from the model as the input encodes and compresses log files. The final compressed artifacts consist of the model, the reference table, and the compressed file. In the following slides, I will introduce each component of ELISE. In step 1, ELISE first converts logs from different sources into JSON format, which makes the processing of different logs easier. Then ELISE does preprocessing with several processing rules to remove log redundancies. We observe that the possible combinations of case in the log file are innumerable. Therefore, in the first preprocessing rule, we can replace case in a log entry with shortcodes. For example, given a log entry, we summarize its case and give the case an identification number. Then we replace the case with the number. This preprocessing could significantly reduce the storage overhead caused by case in log files. Other rules further reduce values in log files. In processing 2, we observe that logs generated by the same session could share values of some properties. For example, logs generated by the same process have the same process ID. Therefore, only keep these shared values once for each session could reduce the cost of storing these values repeatedly. For the given example, ELISE first summarizes log entries into different sessions and finds shared fields in each session. Then ELISE only keeps the values of shared fields once for each session. We also find that values of some fields are innumerable. For example, computer architecture. For these values, we replace them with shortcodes. As shown in the example, ELISE first gets possible values of a key and gives each possible value a short identification number. Then ELISE replaces the values of the key with these codes and reduces the cost of storing the original values. Then rule 3 is designed based on the observation that the values of some fields are increased, for example, timestamp. For these values, we replace them with their offset values. ELISE first analyzes the original log and finds the minimal timestamp in the original log file. Then it replaces all timestamps with the offset between them and the minimal one to reduce the cost of storing non-timestamps. Finally, the last preprocessing rule removes redundancies caused by other frequent words, such as file paths. It removes the redundancies of storing these frequent words by using shortcodes. Given an example consists of 2 log entries. Each entry contains a path. ELISE obtains frequent words and gives each of them a code based on their frequencies. ELISE then replaces words in the original log with these codes to reduce the redundancies. For preprocessing rules designed based on the domain knowledge, can remove log redundancies before the encoding. After preprocessing, we train the deep neural network model on the processor data as the encoder. The model we used consists of 2 LSTM layers, 1 batch normalization layer, and 2 fully connected layers. Given a log file, ELISE trains a deep neural network model to predict each character based on its previous characters. The prediction result contains possibilities of being different characters. Then the deep neural network model tries to make the prediction value of the correct character larger and outputs correct results. After training and obtaining a deep neural network model, given a sequence, a character that needs to be encoded, and the prediction results of this character as the input of the encoder. The encoder encodes this character into shorter representation. Details of the encoding are in the paper. In our evaluation, we collect 13 log files from different systems and applications as our datasets. We first measure the compression ratio of ELISE on different datasets and compare the results with DeepZip and Gzip. We show that ELISE can achieve 13 times better compression ratio on one of our datasets. Then we measure the compression time cost of different methods. The results show that on average, ELISE can be around 6 times faster than DeepZip. To help further understand how different configurations can affect the effectiveness and the efficiency of ELISE, we designed two options. We use different percentage of the whole dataset to train and fine-tune the model. As shown in the figure, using partial data for training and fine-tuning are trade-offs between compression ratios and compression time. We also use the whole dataset to fine-tune the model on different datasets. The results show that fine-tuning the model for one epoch can achieve similar or better compression results than training on the original data for several epochs. More results can be found in our paper. Finally, we conclude that, motivated by the fact that storing logs for large enterprises result in high storage overhead, we designed a better log compression method called ELISE to study redundancies in logs and leverage preprocessing rules to remove them. ELISE also uses a deep neural network-based representation learning technique to train a better encoder. As shown by our evaluation results, ELISE outperforms Gzip and DeepZip by 2 or 3 times in terms of compression ratios, and is around 6 times faster compared with DeepZip. Thank you.